The ideas expressed in the following presentations are those of the speakers and do not necessarily reflect the views of ACI or its committees. ACI web sessions are recorded at ACI Conventions or other concrete industry events and will be made available for viewing free of charge for 1 week. Thereafter, they will be archived on the ACI website or added to ACI's online CEU program, depending on their content. You can earn continuing education credits through ACI's online CEU program. Visit www.concrete.org to register. ACI Conventions provide an opportunity for networking and for keeping up to date with the latest in concrete technology and practices.
So our next speaker is Riyadh Hindi. He's a professor at St. Louis University, and he will be talking about high-strength concrete columns with confined with spirals. Thank you.
Thank you, Halil. If any speaker want to buy out time, I can sell something. Good afternoon. This is a great look at the session. It's really well attended, so I'm glad to be here. Since the subject of this session about high-strength concrete or high-strength reinforcement, so we thought maybe it's a good idea to present a part of our research on bridge columns, basically, but these are columns, and high-strength concrete columns confined with a spiral. So basically nothing out of the blue, nothing new, just experimentally testing some good scale or good size columns under axial load, concentric axial load, but a little bit of creativity in the spiral reinforcement. So I would like to thank my co-author, Lonnie Marble, which he was one of my graduate students. He's working now. And thanks to NSF for partial support on this research. Basically, as I said, it's mainly experimental, axial behavior, talking about the code a little bit, and some theoretical or applications, predicting the capacity and the behavior of concrete using some existing models for confinement. And we have some conclusions to present to you. Well, I mean, the main idea of this research was it's how to confine concrete in a better way, because as you know, the stronger or the higher the strength of the concrete, the more brittle it gets. So it will be some challenges to provide enough confinement to achieve the ductility that we shoot for example, seismic zones where you need ductile columns. Based on what we have in ACI, there is limitation. For example, you cannot, have less spacing pitch of 1 inch or 25 millimeters. If we're in Canada, we have to talk about the metric units as well. So how do you provide that extra confinement if you're not really meeting the limitation by the code? So one option is to, well, this is just a typical concrete. If I wish I had, I think this would have, a regular unconfined concrete. It's really very brittle, as you know. So we want to achieve as much ductility as we can. So it's not really the extra strength, but the ductility that will be very helpful in a seismic zone or for ductile behavior. So we want to achieve as much as we can from ductility or confinement. As you see, when you have a rectangular section or a square section, it's not as effective as if it's a circular section. The hoops or the spiral provide more like uniform confinement, passive pressure. So it confines it and provides better ductility. However, when you have such orientation of the reinforcement in a rectangular column, you see there will be a lot of unconfined core where that won't be as effective as the circular member. So the focus is for the circular member, or most of bridge columns. I don't want to say most, but a lot of bridge columns are circular. So the focus was circular members, and that's how we can use the spirals anyway. So based on the limitation, as we talked about, minimum 25 millimeter, maximum 3 inches. These are the limitations. So what we thought is, to achieve that thing, we came up with using 2 spirals instead of 1, which I'm sure you've heard of that. But we've tested it for regular reinforcement. So instead of 1 spiral, we can use 2 spirals spaced at the same pitch, so you get twice the reinforcement, the lateral reinforcement, or you can double by using 2 spirals, but double the spacing, then you're providing the same amount of reinforcement, but twice the pitch, where it's better and it provides better constructability, especially when you have long columns or long piles. So even that 75 millimeters won't be enough for the concrete to reach down there. So we tested, that's a previous research, 10 in Axial, then we did some cyclic loading, lateral cyclic loading, and then we test the idea also in pure torsion, cyclic torsion. However, this presentation is focusing on the high strength, so everything else was done before was normal strength. Here we're testing 21 high strength concrete. The idea was to achieve 10,000 KSI, which is twice as much as what engineers use these days for normal concrete. And different spacing, and we're talking about regular spiral or a cross spiral. The diameter of the columns were 350 millimeters, which is 14 inches, and their length was 1 meter, which is 4 inches. What we designed to achieve 10,000 psi, 70 megapascal. The actual concrete 28 days was 2 batches. One of them was 67 megapascal and 63. So we weren't very off from our goal or target strength. And that's basically, it's a monotonic axial loading, so this is not a cyclic testing. Here are the reinforcement or the details of the columns. We confined the edges, the ends of the column, so we forced the failure or the crushing in the middle. That's where we instrumented the part, so to make sure that our failure occurred in the instrumented piece. And this is a single spiral, this is a double spiral. So basically, if you have one spiral at distance S, pitch S, if you put another one on the other side, then you're ending with an equivalent one spiral that has S over 2, pitch of S over 2. So basically, this will have twice the reinforcement. But if you double the spacing, then you get the same amount of, equivalent amount of reinforcement. As you see here, we tried to keep the core the same area. So basically, the additional spiral was put at the outer of the initial spiral. So basically, the core or the distance between the longitudinal reinforcement or the diameter of the longitudinal reinforcement kept the same to provide the same moment capacity, right? But we lost some of the cover because of that additional spiral. But here we're talking, I think the spiral was number 3 and reinforcement were number 5. And here you see how they built. This is a single spiral, cross spiral with twice the spacing. So this and this will have the same lateral reinforcement, but this guy will have it twice as much as these two. Okay, this is a summary of the specimens, and you see you have these are the spacings of the pitch. 50s means 50 millimeters, 100x it means cross spiral each will have 100 millimeter spacing, and the last number is the number of the longitudinal reinforcement. So there is also change in the longitudinal reinforcement. We have 8, 10, 12, 14 to see how the effect of the ratio of longitudinal reinforcement on the axial behavior or the confinement, the confined concrete. Okay, so tested the strain gauges we put, and we put LVDTs to measure the displacement in the middle of the specimen, and we also measured the displacement of the head rounds here. So this is how it was set in the lab. And you're talking about 14-inch concrete column. It will give a lot of axial capacity. So we were able to find a place where we can apply that much load to it. And these are the LVDTs. We put two. One had, I think we had 6 inches, and then 12 inches, and 250, actually it's 10 inches and 20 inches. Those are the LVDTs. Plus there were strain gauges on the reinforcement. All right, so these are the now how it crushed. This is a typical crushing, and then once the cover, we loses the cover, the more load will be taken by the column until you fracture the spiral. Once the spiral is fractured, the longitudinal reinforcement will buckle, and then the core will crush. So this is typical failure of the things, and you see here how the the diagonal sliding of the core once everything is lost. So what we're trying to do, we're trying to find how much the core is taking out of that load, because there is load taken by the longitudinal reinforcement, load taken by the cover, and then we want to see exactly how much is the stress-strain behavior of the confined concrete compared to unconfined. So we need to filter that out. So what we did, we take the total force at each time or each strain level. We know the force measured from the testing. We take out how much force will be in the longitudinal reinforcement based on that strain at that level, since we know the behavior of the reinforcement stress-strain diagram. Then we also take out how much force carried by the cover, because we know the stress-strain diagram for the unconfined concrete. We know the area, we can calculate how much force carried by the cover. If we filter those two out from the total force, then we get how much axial force carried by the core. So we do that at any level. If the cover is gone, then you don't have that last term in the equation. And here what we got. So if you compare these three, these will have the same amount of longitudinal reinforcement, 10 bars, but this is a single spiral, 50 millimeter, 2 inches pitch. This is two spirals, each one is 4 inches, so these two will have the same lateral reinforcement. This guy is 2 spirals, each is 50, so it will have twice as much as these guys. And you see how the confinement or the ductility improved, of course, because it has twice lateral reinforcement. But these two, they are very similar in terms of confinement. Well, I mean, there is some differences, but not very significant. However, when you have two spiral, the other advantage that you don't see here, if you lose one spiral, at least you have another one keeps going. So there is a little bit of more indication of the failure. But if you have one, then if it fractures, game over. So this is the unconfined, you see the green, and this is the confined. Here is the steel. So this is the how much we are taking. So this is the total. You take out of it the cover, you take out of it the steel, you end up with the core. So this is the blue one here, not the red. This guy is how much the core is taking force. And this is the total force in the column. So at each strain, you can filter out the reinforcement and the cover. This is more like tabulated results, which these are the three we showed, and you can see how much is the ultimate strain they feel. So this guy, of course, it's higher than these two, and the cross spiral is still a little bit higher than the single, but you know they are very comparable. This is more direct comparison between several columns. These guys is the 50 single, this is the 50 cross, this is the 100. So the same guys, but now they are filtered. We just put them on one figure, and you can see that twice the reinforcement to give you more strength and more. So these are the two, one cross, one single, very similar to each other. Now you can see them all on one page. More results. Tabulated results, and basically again what we're doing, these all have the same number of longitudinal reinforcement, 10 bars. This is 80 cross, 100 across, 110 across, 120 across. So basically all these across. Now the smaller the pitch, you can imagine that it will be more ductile, right? And that's what you're getting here. Same thing, these are all single, so the less the pitch, the more the ductility. And here are, you know, on the one figure, each one of these groups that we just showed. The less the pitch, the higher the. So basically what we're trying to achieve here is to show that the cross spiral, it's nothing dangerous about it, it's just more reinforcement. But you're putting two spirals together. And the beauty about the two spirals, which you know we'll talk about it later, especially when you have torsion. I know not too many columns will be subjected to torsions, but there will be cases where you get significant torsion in a column. When you have a asymmetric bridge bend, or there is an eccentricity between the center of the bend and the center of the roadway. And in buildings, you get some torsion in the columns. It depends on the, twisting mode of vibration. And so when you have two spirals, you can imagine that the torsion behavior will be more symmetric in both ways. But when you have one spiral, it's like you have one spiral. You can really twist it in one direction easily, the other direction no. So you get that asymmetrical behavior when you have one spiral. But here we're not really presenting any torsion. That was done earlier. 4 minutes? Okay. This is more results. I don't want to go through it. I'm not sure if they will upload the presentation online, but I gave them permission. If anyone wants a copy, I can send them. This is more results. This is here we're investigating the effect of longitudinal reinforcement ratio on the confinement, how much it affected the confining the concrete, right? I think the table before that, the longitudinal reinforcement. Here, if you see for each group, the spacing of the pitch is the same across all these across. Now the number of longitudinal reinforcement. As you can imagine, the effect of reinforcement, longitudinal reinforcement on confinement is not very significant. So that's something also made us feel good because we're not getting really weird results. It's not really the amount of reinforcement, it's the detailing of the longitudinal reinforcement. I may be able to live with better confinement if I choose more rebars than making them bigger rebars, because I'm just providing better support for my confinement or lateral reinforcement for that passive pressure. Okay, so that not bad. And then now what we're trying to do is to define the ductility. Well, we defined it in a way here that it's just the strain ductility, because we're looking for the stress-strain behavior of the confined concrete. So we said, well, our ductility, we defined it, it may be wrong the way we defined it, but at least a measure for us to compare apples to apples. So our ductility is the crushing strain for the confined concrete compared to the crushing strain of the unconfined concrete, just to give you that nice ratio where you can compare. Okay. So here you can see how much is the ductility when you have the cross spiral S, cross spiral 2S, and single spiral. So these two, the blue and the red, will have the same amount of lateral reinforcement, one single, one across. The green will have it twice as much as these, but also in cross. So you can see how more ductility the cross spiral either way provided, but some cases a little up, some cases a little down. So then we said, well, let's see what we can do in terms of analysis. Well, we have 2 minutes, 1 minute, okay. So we picked, we didn't do any theoretical modeling, or we didn't come up with our model. So what we did, we used what's existing, which you all know. Mander is one of the well-known models people use. But that was, proposed or designed for normal strength concrete, not high strength concrete. So then we used Ravzi and Sacholo, and also we used Bing. Bing was designed for high strength. This guy was also by Ravi and Sacholo for high strength, but Mander's one, was for normal concrete. Because we did test some normal concrete before, so we thought we'll use them. And here what they come, I think here it's really hard to see the numbers, but basically what we can see here, it's, for example, here this is the Mander, which is usually overestimates the behavior of confined concrete, but again, that was for normal, so you can't really blame the model. And the other two, they were very close to the experimental, and they worked really fine. So what we did for a cross spiral, we couldn't find any model for a cross spiral. We used the one available, which is Bing and Sacholo. But what we did, we doubled the reinforcement. So we just say, well, the S is half if we have, just to make them more. So the other two models work fine. The shape of Mander is okay, but it's just over-predicted. Again, that was for normal. So far, I think everything looks good, and we were able to confine the high-strength concrete, and the results looks fine, and we got the increase in ductility, and it looks like I'm out of time, so if you have any questions, I'd be happy.
Again, we have time for one quick question.
Looking at your curves, I'd like to know your testing was strain control or load control or stress control?
We tried to follow the strain control, but the machine, it was a little bit an old-fashioned machine, but we did follow the displacement control. That's how we designed it. Displacement control, not it's strain, but displacement.
Thank you.
Thank you, Riyadh. Thank you very much.